right. Next section, 6-3. Want to say it?
Proving that a quadrilateral is a parallelogram. Page 303.
I think it's funny that you added the page. Okay,
Oh, you
so
did page before.
no, I don't always. Okay, so anyways, let's do. I'm gonna do like a geoboard type thing. There's an exercise. If you happen to have a geoboard at home, great. Use it. If not, just take a look and just watch and enjoy. So it's saying here, if I were to make some rubber bands. So imagine I'm putting rubber bands on here, not just these little, this thing. So let's see, I'm going to make it kind of small so that I can actually count it relatively easily. So here we have from there to there, I'm going across 2, 4 little, did it go away? Oh no, it's there. Okay, so I've got that one, and then let's say I put another one here, and then go across that way, so that I'm cutting the red line in half, and I'm gonna go diagonal 1, 2, 3, 4, 5, 6. I'm a little bit past there. Let's see if I can. Yeah, no, I won't bother. Okay, so I have these rubber bands, imaginary rubber bands, put on my geoboard, right? Both lines bisect each other or cut each other in half. What would happen if I connect the, let's see, what color do I have on here? What would happen if I connect this corner with this corner and all the way around? What do you think? What will I create? Do you know?
Parallelogram.
Yeah, I will actually. So if I move this up, not what I want to do there. I want to move this one to here and this one to the corner like that. And then I'm gonna trace it. Use another fun color. So right there, do the same thing with this side. Isn't this such a fun little tool? Mm-hmm. So what am I creating? Lily, you said it. A parallelogram, right. So if we have, what's that? What did you say that, Hannah?
I'm confused what you're doing.
I'm connecting the corners of my rubber bands. And look what I'm creating as I do so.
Oh, I see what I mean.
So what could we say about parallelograms and their diagonals?
Equal. Oh no, they bisect.
They bisect each other, right. So if I get rid of this diagram here. So in a parallelogram, if I can say that I have this, right? Something like that. So there's a whole bunch of theorems I'm going to run through. There's 2 in the beginning, and I'm not going to actually write out the proofs at the request of these beautiful ladies here. But I will talk through them, so you're not totally free of listening to the proofs. So here's the first one, though. It has to do with the diagonals. It says, if the diagonals of a quadrilateral bisect each other, then the quadrilateral is a parallelogram. So if I know that those hash marks, those green information in there, that each of the diagonals are bisected, then I know that the quadrilateral is a parallelogram. That's what this theorem is. There's not a name for this one either. If the diagonals, O-N-A-L-S, diagonals of a quadrilateral bisect each other, then the quadrilateral, I'm going to abbreviate quad. Is that okay with you all? Mm-hmm. Okay, good. Quadrilateral is a parallelogram. So we could prove this, right? And I told you I'm not going to go through the proof, so I'm going to use my little diagram that I have here, and I'm going to talk about it though. So if I'm given that the diagonals bisect each other, and they're in your book, there's a diagram like this that has it labeled A, B, C, D, and E in the middle. So if I'm given that AC bisects BD, in other words, I'm given the information on there, the segments are congruent, then I want to prove that it's a parallelogram. How can I do this? Do you know? What do you know? What's in the middle of this?
The bisect.
What kind of angles?
Right angles.
Not right angles. They form an X.
Vertical.
Vertical angles. I have vertical angles. So if I said like in here I have this angle and this angle are congruent, right? Look it. I have a side, an angle, and a side. A side, an angle, and a side. What kind of triangles do I have?
Side and
Right
side.
here. Yeah, I have two congruent triangles, right? So by side, angle, side, I have, we could call this triangle 1 and 2. Triangle 1 is congruent to triangle 2, right? You could name it by the sides of the vertices also. And then by CPCTC, we have congruent sides, right? Sides are congruent, right? So I could do the same exact thing for triangles 3 and 4, the side two triangles. I can prove that those two are congruent to each other also by SAS.
Yeah.
And then I could also then prove that this side is congruent to this side by CPCTC. So I now have opposite sides of a quadrilateral that are that are congruent, right?
Yeah.
What did we know from way back here of our parallelogram stuff? What do we have to know about the opposite sides right there?
Yeah, they're equal.
They are congruent.
They're congruent. Opposite sides are congruent, right? So I actually already put the diagonal lines thing in here, and I think we did that because of something else from the previous section. I don't remember what the theorem was. But we have in here that parallelograms have bisecting diagonals. The diagonals bisect each other, right? So you can add this to that diagram. Go find it, dig it out. Add in here in a parallelogram
Oh.
diagonals bisect each other. Hannah somehow already has it. I don't know what this thing is. What is that?
I have no clue.
I don't either.
Can't erase it either.
No, it's not. It's not moving. I don't know what this is. I'll have to play with it later.
Wait, do I already have that too?
What is that?
It's like orange.
I know. I don't know why it's not going away. Okay, so we have that diagonals bisect each other already, right?
Mm-hmm.
Okay, that's one of the theorems, and we kind of talked already about proving that their opposite sides are congruent, so that you could also say, too, to show that it's a parallelogram within this proof that I'm not actually doing it as a proof, I'm talking through it, right? Let me switch colors again on you. I don't have another color. Red, dark red. So by CPCTC, I also have this angle here at the bottom right is an alternate interior angle with that one. They're congruent by CPCTC. Since alternate interior angles are congruent, then the top and bottom lines are parallel. You could do the same thing with the other sides, saying that these lines here, these angles here, are alternate interior angles that are congruent by CPCTC. Therefore, those sides are also parallel. So we have proven then that this is a parallelogram, meaning that opposite sides are parallel. Okay?
Mm-hmm.
Okay, another theorem. Kind of like the grid, actually. It kind of helps me stay writing a little bit more neatly. Maybe. All right, if one pair of opposite sides of a quadrilateral is both congruent and parallel, one pair of opposite sides, I'm going to write it. If one pair of opposite sides of a quadrilateral is both, I'm underlining, both congruent and parallel, then the quadrilateral is a parallelogram. So in other words, if I do a quick sketch, something like this, great. It says if one pair, just one pair, doesn't matter about the other. If I have one pair that is both parallel and congruent, automatically then, by this theorem, we have a parallelogram. So just because one pair the top and the bottom are parallel and congruent, that will make these also parallel, the side
So a
ones.
square is a parallelogram.
Yeah, a square is a parallelogram.
So everything under the chart is. Okay,
Yes, yes. So Lily, you just made a kind of a good discovery. Maybe you also have realized this or not. When you're working down this chart, and don't write this on your chart, I'm just gonna show you. As you're working down this way, everything down here has all the properties above it. The things up at the top have only the properties at the top. As you work down, they
complex.
They get more complex, right? They have more and more and more properties that are included that make that square a square, or make that isosceles trapezoid an isosceles trapezoid. Let me get rid of all this stuff now, because I don't need that. There, okay. We will come back and add more stuff to this. Wait, we already have the opposite sides in this one. You can point to it if you want to, right here and right here. Opposite sides are congruent and parallel. It's on the diagram, but now we have it in words too if you care, okay? And that would then be true of everything below the parallelogram. That's true of the rectangle. That's true of the rhombus. That's true of the square. Does that make sense? Okay. I'm gonna quickly turn my thing into airplane mode so you don't all get to see my texts that come in. Okay. So example 1. Let's try one.
Woohoo.
There's only 3 examples. There's just 4 theorems in this section.
Good
Okay.
thing I don't like this.
So finding values within a parallelogram. So it's just like, let's throw some algebra in here at you. Keep practicing it so you don't forget it, right? Find the values of, x and y for which MLPN must be a parallelogram. In other words, make it so that it's true of a parallelogram. So here's my diagram. I actually really like having these dots here. I can draw out like straight lines. I'll have to keep doing this. You know, you all think I'm nuts, don't you? That's because I am.
I don't even like see the lines the way I see the screen, the dots on it.
Oh, really?
I don't know, I have to like
interesting.
look over at the top.
Oh,
and
because there's a
see
little
it.
bit of a glare on the screen. Okay, so they have the diagram, has the diagonals drawn in, and it has expressions for each segment. So the top left is 2y minus 7. The bottom right is y plus 2. The bottom left is 3x. The top right is x plus 5. Don't let the 2 different variables scare you. So what must be true if it's a parallelogram? What did we just learn?
That 3x equals x plus 5.
Right. So from the corner to the center, the M, I didn't label it, M, L, P, N. So from M to the middle must equal from the middle to P. So we can solve that one. So 3x equals x plus 5. Unwrap your package. In order to do so, you need to get the variables to one side. Subtract x, subtract x. I'm left with 2x equals 5. Then what?
Divide by 2.
Divide by 2. Yeah, so you have x equals 2.5. You could write it as 2 1/2, and you could also even leave it as 5 over 2. I don't care. They're all equal. They're all simplified as far as you can. It doesn't matter to me. So we have one more to do. We did the x's. Now what about the y's?
They equal each other too.
They also equal each other. So in my diagram, I'm going to put little hash marks to remind myself of why I'm doing this. 2y minus 7 equals y plus 2. All right, what are we going to do first?
I always add 7.
So I'm going to suggest, just for the sake of like keeping things consistent, move your variable first. Get the variables to one side first. It doesn't really matter. It will end up the same. Tends to cause less confusion. So I have y minus 7 equals 2. And then you wanted to add 7. Is that okay?
Yeah.
Okay.
I always do it this way though.
That's okay. As long as you have a consistent way so you don't mess yourself up, I don't care. Y equals 9. And you can check these, right? How can I check these?
See what they end up equaling.
Yeah,
Put it
well,
in
so
for-
right, so I can put this 9 in
So
for
9
y
plus
there.
2.
Yeah, what's 9 plus 2?
11.
So you might be asked, what is that measurement, right? So this is 11. And then what's 2 times 9?
Right. 7.
18.
11.
Minus 7 is 11, right? Okay, what about the x's?
They both
3
equal
times
7.5.
2.5.
Right, so 3 times 2.5 would be what? What'd you say?
7. Or 7.5, sorry.
7.5. Okay. And then
2.5
2.5 plus 5 would be 7.5. Oops, 7.5, not 75. Yeah. Okay. Yay.
Yeah.
Okay.
I did
What?
one of these in the examples.
Yeah, no,
last
it was
time.
in the apply your skills last time.
Oh,
I did this
okay.
exact problem today.
That's
Uh-huh.
funny. The same exact numbers? Or just the
No,
same idea?
same-
Same
like,
idea.
Yeah.
It was hard. It had 3 variables.
Ah, system of equations.
Dude,
I like those. You know me. Okay, next theorem. We have 2 more and then 2 more examples, okay?
Confirm for that.
And I'm gonna, you have room to write the theorem. I'm gonna talk through the proof of it. I'm not gonna do the proof. So if both pairs, so now we're talking both pairs of opposite sides. Both pairs of opposite sides of a quadrilateral are congruent, then the quadrilateral is a parallelogram. So how do we know this? I'm not going to make you write out the proof, but if you want to sketch out some stuff that I'm doing to show you how do we know that this is true. So give yourself a quick
I feel like we
parallelogram.
did this proof thing already.
We did something similar.
So it's like, would it be a rhombus then? Or
Not necessarily. So we just know that both pairs of opposite sides are congruent. So if I say like this top is congruent to the bottom and the left side is congruent to the right
Oh.
side. Sorry, I didn't mean to do the 2 there, I meant 1. So there. So if we know that, that's what I'm given. Okay, so I could then in my proof say draw the diagonal. I'm going to label this real quick.
So you can say it's equal to itself.
Right. So I could say, because I can say in the proof, I could say draw diagonal XZ.
SSS.
Yeah, you're getting ahead, right? So we know that that side is congruent to itself. We have 2 other pairs of congruent sides. So we have, if I number these triangle 2 and triangle 1, I could show that triangle 1 is congruent to triangle 2 by SSS, right? Since I know that, by CPCTC, I could show that this angle and this angle are congruent to each other because they're the corresponding parts, right? So I could label that A and B. I could say angle A is congruent to angle B by CPCTC, right? Because I have that, I can then say that XY is parallel to WZ, right? Because of alternate interior angles. Does that sound familiar? I can do the same exact setup here for the opposite pair of sides where I'd say something like angle BC is congruent to angle D, right? Because again, of CPCTC, I'm not going to write this part out, because those are congruent, they are alternate interior angles that are congruent, so therefore I have opposite sides again that are parallel, right? So I have proven then that it is a parallelogram because opposite sides are both parallel. So if we know both pairs of opposite sides of a quadrilateral are congruent, then we know it's a parallelogram. And in our diagram thing, this one, we had opposite sides that were congruent, right? I don't really need to put that in there. Is that okay with you? Okay. All right. Because we already had it. Did I? Oh, no. Man, I skipped a lot of space there. Okay, so the next theorem, if both pairs of opposite angles of a quadrilateral are congruent, then the quadrilateral is a parallelogram. So if I know this, let's see. Ooh, that was an ugly one. Hold on. Let me try that again. There's my parallelogram. So if I know this, that opposite sides are congruent, opposite angles are congruent, then what it's saying is that I would know that opposite sides are also parallel. Right? Okay. So how would we know that one? I'm going to talk through a proof real quick.
Line again if you want. If
You could
did,
draw the
yeah.
diagonal line again,
But
yeah?
do you need to? Because you already have a side angle side.
Where do you have, what do you mean
Well,
side angle side?
If you, I don't know.
If you put it in there, you'd have side angle side, right?
Mm-hmm.
Okay, so I could show, yeah, you could if I change my colors real
Or
quick
is
here.
there something else?
No, that's one way to do it for sure. So, I would have, well, what do I want to do with this one?
Because we haven't really proved these ones. We've been proving triangles, so I know how to do
Right.
it. Put that triangle line.
Yeah. Hold on a second. Oh, this is part of your homework. So you get to do that for your homework.
What?
I'm gonna leave it at that
Put the line
to
for
prove
the
this one. It's
triangle.
number 19. I want you to do number 19. Huh? It's done. It started for you.
Oh.
It started. It's a
Oh,
fill in the
yeah,
blank
yeah,
kind of
yeah.
proof. So I want you to do.
Yeah.
So I'm number 19 is homework. If I didn't put that in the list, add it to the list. Okay, circle it now in your book. Go ahead.
Circle
Number
the
19.
line.
Is there? It already is
Mhm.
circled. Oh, good. Look at that. I was thinking.
Yay.
Okay.
Just love
All right.
this.
So
Oh, it's a fill in the blank one, so you can't tell them to draw the line.
right, it is fill in the blank one, but that kind of helps you guide your thinking through it if you're not quite sure still. Okay. Example 2, and then 3, and then we're done. Example 2 is this one: developing a proof based on the information given. Can you conclude, or can you determine that the quadrilateral must be a parallelogram? And then you need to explain. Don't forget that part. It's more for your benefit of understanding this for real and also developing the proof and reasoning skills. Okay, so I'm going to try my best at drawing these nicely. Not A, not B. I want A first. No. Stop it. Okay, there. That's what I had to do. Okay, A. Oh, that's what that is.
You still
Good to
got your
know.
little circle over there.
I do still have that circle over there. Okay, pen back. A. Here's my attempt at a decent parallelogram. Here's my parallelogram, and then the diagram has that diagonal in there, and then it has some other information about angles. That.
Well, yeah, you can do angle,
This.
angle.
There's no such thing
wait,
as
wait,
angle,
wait,
angle,
no.
angle.
Angle, side angle. Because this is itself.
Okay, you could prove that they're sure. So this is one you're saying. I could say what, Hannah?
Well, you can say this is itself congruent to itself.
Okay, so you could say this here.
Reflexive.
That's congruent. Sure, reflexive. So you have two congruent
You
triangles.
can do angle,
Which-
side angle.
So by ASA, you could say that you could label it 2 and 1. Triangle 2 is congruent to triangle 1. Okay, but why does that help you? You're making it
Trying
more
to-
difficult, by the way.
Oh,
Wait,
no,
What?
don't do that.
Isn't
Don't
this
do
one
that.
just parallel?
You,
Don't
well,
do
we don't know that. You don't want to do it this way?
But
Okay, this just
because-
makes it harder. But wait a minute. Make life easy. Hold on. Look at this. That one is congruent to that one. So that's some
it's
number.
alternate
Let's call it
interior
X.
angle.
No.
'Cause you could, like,
Yeah, you could.
say
You
that
can
they're
say it's,
parallel, and once you know they're parallel, you can do that theorem.
you
thing.
can. You could say that angle there that I said X is also their X, right? So you could say that this is parallel because of alternate interior angles. And then you could say the opposite also of saying, well, then if this maybe is Y and then this is also Y because they're congruent. Therefore, you have alternate interior angles and therefore you have,
Parallel.
you do. What I was thinking of is look at X and Y right here. X and Y add up to this angle, right? X and Y add up to this angle. So aren't the opposite sides here angles congruent? Aren't those opposite angles congruent? Oh, and aren't these opposite angles congruent? Oh, so we could also say, yes, both pairs of opposite angles are congruent, which we never did add to that diagram, by the way. I'm gonna scroll up there real quick. Go to your diagram. Oh, we did have it in there, huh? I don't know when we added that, but yeah, opposite angles are congruent.
I think there's already.
And you can even add in there opposite and opposite angles are congruent. We've added a lot already, right? I told you we'd keep coming back to this thing. Okay, we were here. So yes, both pairs of opposite sides are congruent. There's a lot of ways with the given information that you could have proven that this is a parallelogram. You could have used the angle side angle to prove opposite sides are congruent. When both pairs of opposite sides are congruent, then you have a parallelogram. That was one of our theorems. When you know this, opposite sides are congruent, both pairs, then you know you have a parallelogram. There's lots of different ways for this particular one. How about this one? So I'm going to draw another.
It's gonna be no because it's just gonna be that way. There's two of them.
It's gonna be no. It's always no.
How about this one?
And it's no just because the sides aren't opposite from each other.
Right, the two pairs of you have two pairs of congruent sides, but they are not opposite. Right. So no.
Not opposite sides congruent.
Yeah, opposite sides are not. So I could draw the congruent sign with a slash through it, meaning not congruent. It could be a kite. Remember the kite thing?
Yeah, it's just
Yeah.
a weird shaped guy.
It is a weird shaped kite, but it could be because you have two connected sides, adjoining sides, adjacent sides that are congruent. Okay? Last one, example 4. It's a real world one.
3.
Yeah, sorry, example 3. Thanks, Annalise. Example 3, I owe you a piece of candy. Catch my mistakes, right? A parallel ruler is a navigation tool that is used to plot ship routes on charts. It is made of 2 rulers connected with congruent crossbars. There is a picture of it, so I'm going to try and draw something real quick, just a sketch of it. So let's say you have a ruler here and a little like hinge thing here and a little hinge thing here, and you have then another ruler here and here, and then there's these little cross pieces that connect these, like a hinge almost. Imagine Legos or Connects or Rector set, anything like this. So this piece here is congruent to this piece here. So as you shift maybe this arrow, that ruler that way, and this one that way, the angles here will change, right? So the angles here will change, and they'll always be changing at the same amount, right? What have I created inside of here? Let me change the color.
A parallelogram.
How do you know that this is a parallelogram?
Because you got the congruent sides.
Yeah, so opposite sides are congruent here, 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 right? So if I finish reading what it says in here, now that I've had this little sketch, I can talk about it. It's made of 2 rulers connected with congruent crossbars. Those were my crossbars right there, right? So that, or such that, I didn't label it, A, B, C, D. So that AB across here is equal to DC. We said that. That was this part here. They're congruent. And AD, the crossbar pieces here, are congruent to each other also. You place one ruler on the line connecting the ship's present position to its destination. So like let's say the ship is here. Hey, color. It froze. Put the ship here. You then say, where was I? You place the ruler on the line connecting the ship's present position to its destination. Let's say over here, there's where you're going, right across there. Then you move the other ruler into the chart's compass. So like there's somewhere along here a compass where it says north, south, east, west. Hopefully you all know those directions. And then never eat soggy waffles. Is that what you're thinking, Hannah?
No, I was just thinking Lily's gonna say she doesn't know.
Okay. Then you move. Okay, then you move it to the compass, the chart's compass, to find the direction of the route. Explain why this instrument works. Well, how do you know it works? So if you can connect this to there.
What?
So I didn't draw it great. So let's say this is my destination, and somehow let me get rid of this thing. Okay. So let's say then that my compass is down here, and here's the center of it, and there's your cross north, south, east, west stuff, right? North, south, east, west. This could tell you, this part right here tells you kind of why does this part here tell you what direction you're heading?
Oh, because it'll go line up with that.
It will line up with this, which will line up with your direction of travel, right?
Yeah.
So if you can put on with this little navigation tool where you are to where you're going, and then move this one so that it lines up with the compass on the map, then you can figure out what direction you're heading. Does that make sense?
Could do that.
Guessing it's not something that you're ever really going to do on your own, but it is something that is useful if you are actually sailing out in the middle of the ocean, because you cannot see land. It's amazing how far you can see, and yet you can't see the curve of the earth. It's just not possible. It's too big. Okay. Questions on any of this?
Nope.
Okay. We're finished with the section, but we're not finished for the day. We have a second section today. At least you all do. All right. Thanks for joining us.
Have a nice life.